Welcome to Engineering Physics, a comprehensive course designed for first-year B.Tech students. This course covers the fundamental principles of classical and modern physics that form the foundation of every engineering discipline. Let us begin our exploration of the physical world that powers. Here is the outline of our course. We will journey through a wide range of topics, starting from units and measurements, moving through waves, optics, quantum physics, semiconductors, and modern materials, and finally reaching engineering applications such as renewable energy. The objectives of this course are fourfold. First, we aim to build a strong conceptual foundation in both classical and modern physics that supports engineering practice. Second, we develop the mathematical sophistication needed to model physical systems accurately. Third, every principle will be connected to a real engineering application or device. Finally, the course prepares you for university examinations and also nurtures research-oriented thinking. Our pedagogy follows a clear pattern: definitions, principles, derivations, worked examples. For deeper study, several reference textbooks are recommended. Halliday, Resnick and Walker for fundamentals, Arthur Beezer for modern physics, Griffiths for electrodynamics and quantum mechanics, Ajoy Ghatak for optics, Charles Kittel and S. O. Pillai for solid-state physics, and Pandey, Chaturvedi, Malik and Singh for engineering physics. These texts will complement our lectures and provide additional. We now begin our first section on units, dimensions, and errors. This foundation will allow us to measure, compare, and verify physical. A physical quantity is any property of a system that can be measured. Physical quantities fall into two categories. Fundamental quantities are independent and include length, mass, time, electric current, temperature, amount of substance, and luminous intensity. Derived quantities such as velocity, force, and energy are combinations of these fundamentals. The International System of Units, known as C, defines 7 base units from which all the 7 C base units are the meter for length, the kilogram for mass, the second for time, the ampere for electric current, the Kelvin for thermodynamic temperature, the mole for amount of substance, and the candela for luminous intensity. Since 2019, all 7 units are defined in terms of fixed numerical values of 7 fundamental constants of nature, such as the speed of light, Planck constant, and elementary charge. This makes the definitions universal and reproducible. The dimension of a physical quantity tells us how it is built from the base quantities. We use bracket notation with symbols for mass, length, time, current, temperature, amount, and luminous intensity. For example, velocity has dimensions of length per time, force has dimensions of mass times length per time squared, and energy has dimensions of mass times length squared per time squared. Such dimensional formulas provide a powerful consistency check. Dimensional analysis has 3 main uses. First, it checks whether a physical equation is dimensionally consistent. Second, it helps derive relationships between physical quantities. Third, it converts units between different measurement systems. The principle of homogeneity tells us that every term in a correct physical equation must carry the same dimensions. For example, the kinematic equation relating final velocity, initial velocity, acceleration, and distance can be verified by comparing dimensions. Dimensional analysis is powerful but limited. It cannot determine dimensionless constants, such as the half factor in kinetic energy. It fails for equations containing transcendental functions like sine, cosine, or exponential. It cannot distinguish quantities that share identical dimensions, like work and torque. Moreover, it does not capture the vector nature of physical quantities. These limitations remind us to use the method as a check rather than a substitute. An error is the difference between the measured value and the true value of a physical quantity. Errors are broadly classified into three categories. Systematic errors arise from consistent bias, often due to instrument calibration, environment, or observer habit. Random errors fluctuate unpredictably and can be reduced by averaging many measurements. Gross errors are human mistakes in reading or recording the data. Understanding these categories is essential for assessing the reliability of. When we repeat a measurement many times, we extract statistical information from the data. The mean represents the best estimate of the true value. The absolute error of each reading is its deviation from the mean. The mean absolute error averages these deviations. Relative error normalizes this by the mean, and percentage error expresses it as a percentage. Together, these quantities tell us how trustworthy. When physical quantities combine, their errors propagate to the result. For sums or differences, the absolute errors add. For products or quotients, the relative errors add. When quantities are raised to powers, the relative error is multiplied by the absolute value of the exponent before adding. These rules help us estimate the uncertainty of any derived quantity. Let us consider a simple pendulum experiment used to measure gravitational acceleration. Given the length and time period along with their uncertainties, we can compute the value of g. Applying the propagation rules, the relative error in g is the relative error in length plus twice the relative error in period. In this example, we obtain g equal to 9.87 meters per second squared, with an uncertainty of roughly 3%. This worked example shows how every measured input contributes. Significant figures express the precision of a measurement. All non-zero digits are significant. Zeros between non-zero digits are significant. Leading zeros do not count, while trailing zeros after a decimal point do count. For arithmetic, addition and subtraction follow the smallest number of decimal places, whereas multiplication and division follow the smallest number of significant figures. These rules ensure that our results do not falsely claim more precision. Let us summarize this section. 7C base units underpin all physical measurement. Dimensional analysis verifies and derives equations, but cannot fix dimensionless constants. Errors come in systematic, random, and gross types, and combine through well-defined propagation rules. Finally, every reported result must be written as a mean value with its associated uncertainty and the correct number. Here are some likely university questions on this topic. You may be asked to state the principle of homogeneity of dimensions and verify a kinematic equation. You may need to differentiate systematic and random errors with examples. Another typical question is the derivation of percentage error in G from a simple pendulum. You should also be able to discuss the limitations of dimensional analysis and use it to convert units between the C. We now move into the section on waves and oscillations. This area forms the basis of countless engineering applications, from mechanical vibrations to sound and. Periodic motion is any motion that repeats itself at regular intervals of time. A special and very important case is simple harmonic motion, often abbreviated as SHM. In SHM, The restoring force is directly proportional to the displacement and always directed towards the mean position. This linear restoring behavior makes SHM the building block for understanding. Applying Newton's second law to a mass under a linear restoring force gives the differential equation of SHM. Its solution is a cosine function of time. Three parameters describe this motion: the amplitude, which is the maximum displacement; the angular frequency, which sets the period and frequency of oscillation; and the phase, which encodes the initial conditions. Together these define. In simple harmonic motion, the energy continuously transforms between kinetic and potential forms. Kinetic energy is largest at the mean position, while potential energy is largest at the extremes. However, the total energy remains constant throughout the motion. Importantly, this total energy is proportional to the square of the amplitude. Doubling the amplitude therefore quadruples the energy. This graph shows the displacement and velocity of a simple harmonic oscillator as functions of time. The blue curve represents displacement, while the red curve shows velocity. Notice how the displacement leads the velocity by a quarter cycle. When displacement is maximum, the velocity is zero, and when displacement passes through zero, velocity reaches its peak. This phase relationship is a hallmark of all real oscillators. Do not vibrate forever because of frictional or viscous losses. A damping force proportional to velocity introduces a new term into the equation of motion. The behavior now depends on how damping compares with the natural frequency. If damping is weak, we get under-damped oscillatory decay. At critical damping, the system returns to equilibrium most rapidly without overshoot. If damping is strong, the motion is over-damped, returning. In the under-damped regime, the motion is an oscillation whose amplitude shrinks exponentially with time. The angular frequency is slightly less than the natural frequency because damping pulls it down. The graph shows this clearly. The oscillations continue, but they are enveloped by a decaying exponential. This is the typical behavior of mechanical vibrations, electrical circuits, and the quality factor, denoted Q, measures how lightly damped an oscillator is. A high Q means very low damping and a sharp resonance peak. The logarithmic decrement quantifies how the amplitude decreases from one cycle to the next. It can be obtained simply by comparing the heights of successive peaks in a decaying oscillation. Both quantities give us practical measures of how energy is dissipated. When an external sinusoidal force drives an oscillator, the system reaches a steady state at the driving frequency. The amplitude of this response depends on how close the driving frequency is to the natural frequency. At a specific frequency called the resonance frequency, the amplitude becomes very large. This has crucial engineering implications. Bridges, buildings, and mechanical assemblies must always be designed to avoid driving frequencies near resonance. These resonance curves show the amplitude response of a driven oscillator against the ratio of driving to natural frequency. When damping is small, the curve has a tall and sharp peak at resonance. As damping increases, the peak becomes shorter and broader. For very large damping, the response is almost flat with no clear resonance. This is why engineering structures are deliberately given enough damping to suppress danger. A traveling wave on a stretched string obeys the one-dimensional wave equation. Its speed is set by the ratio of tension to mass per unit length. The general solution is the sum of a forward traveling wave and a backward traveling wave. A harmonic wave is characterized by its amplitude, wave number, and angular frequency. Importantly, a traveling wave carries energy proportional to the square of its amplitude and the square. When two waves of equal amplitude travel in opposite directions, they superpose to produce a standing wave. The result is a stationary pattern with fixed nodes and antinodes. Nodes are positions of zero displacement, while antinodes are positions of maximum displacement. For a string fixed at both ends, only certain wavelengths and frequencies fit. This quantization of modes is the physical basis of musical instruments and many resonant cavities. Sound waves in air are longitudinal pressure variations. Their speed depends on the bulk modulus and density of the medium. Sound intensity measures the power carried per unit area. Because human hearing covers an enormous range, we express sound levels on the logarithmic decibel scale, referenced to a threshold of about 1 picowatt per square meter. This logarithmic measure aligns better with how the Doppler effect describes the change in observed frequency when source and observer move relative to each other. A common formula combines the velocities of source and observer with the wave speed in the medium. Engineering applications of the Doppler effect are widespread. Radar guns measure vehicle speeds, Doppler ultrasound visualizes blood flow, and astronomical redshift reveals the motion of distant galaxies. It is a beautiful example of how a simple principle finds a pure monochromatic wave travels at the phase velocity, defined as angular frequency divided by wave number. However, real signals are wave packets built from many frequencies, and their envelope moves at the group velocity. This distinction matters because information and energy actually travel at the group velocity, not the phase velocity. In non-dispersive media the two are equal, but in dispersive media such as optical fibers, plasmas, and water waves they differ. Remarkably, for matter waves, the group velocity equals the speed of the associated particle, beautifully linking quantum mechanics. Let us summarize this section. Simple harmonic motion is governed by a linear restoring force, with total energy proportional to the square of the amplitude. Damping introduces an exponential envelope and produces three distinct regimes. Resonance occurs near the natural frequency, and its sharpness is measured by the quality factor. Waves transport energy at a speed set by the ratio of restoring force to inertia. Finally, the Doppler effect links the motion of source or observer. Here are some typical exam questions for this section. You should be able to derive the differential equation of a damped harmonic oscillator and discuss its three regimes. Define quality factor and logarithmic decrement and relate them. Derive the resonance amplitude formula for a driven oscillator. Obtain the speed of a transverse wave on a stretched string. Prove the relations for nodes and antinodes in a standing wave. Finally, derive the Doppler formula when both source. Our next section explores the interference of light, an elegant demonstration of the wave nature of light with many engineering applications. Maxwell showed in 1865 that light is a transverse electromagnetic wave. Visible light covers wavelengths from about 400 to 700 nanometers. When two beams from coherent sources combine, their electric fields add linearly. This produces a pattern of bright and dark regions known as interference. Two sources are coherent when they emit waves of the same frequency with a constant phase relationship. Coherence is the cornerstone of for interference fringes to remain stable and visible, Several conditions must be satisfied. The two sources must be coherent. Their amplitudes should be nearly equal so that dark fringes are truly dark. The sources should be narrow and placed close together. The background should be dark for high contrast. Finally, the polarization states of the two beams should match. When all these conditions are met, we observe states consider two electric fields with equal amplitude but a constant phase difference. Adding them gives a resultant whose time averaged intensity depends on the cosine squared of half the phase difference. Maxima occur when the phase difference is an even multiple of pi, giving 4 times the single source intensity. Minima occur when the phase difference is an odd multiple of pi, giving 0 intensity. This intensity formula is the foundation of Young's double-slit experiment is the classic demonstration of light interference. Light from a coherent source passes through two narrow slits and produces overlapping waves. These waves meet on a screen and create bright and dark fringes. For a point at height y on the screen, the path difference between the two waves is approximately the slit separation times y divided by the distance to the screen. This geometric relation directs bright fringes appear where the path difference is an integer multiple of the wavelength. Dark fringes appear where the path difference is a half integer multiple. The spacing between consecutive bright fringes is called the fringe width. It equals the product of wavelength and screen distance divided by the slit separation. This simple expression makes Young's experiment a practical tool for measuring wavelength, refractive index, and let us consider an example with a slit separation of half a millimeter, a screen distance of 1 meter, and a sodium yellow wavelength of 589 nanometers. Plugging these values into the fringe width formula gives a fringe spacing of about 1.18 millimeters. So consecutive bright fringes will appear roughly 1 millimeter apart on the screen. This is large enough to observe easily without light reflecting from the top and bottom of a thin film produces interference. The total path difference is twice the film thickness times the cosine of the refraction angle plus an extra half wavelength shift due to reflection at the denser medium. Maxima and minima in the reflected light depend on this combined path difference. This explains the brilliant colors seen in soap bubbles, oil films, and thin coatings on when a plano-convex lens is placed on a flat glass plate, an air film of varying thickness forms between them. Interference produces a pattern of concentric bright and dark rings centered on the point of contact. For dark rings in reflected monochromatic light, the radius of the nth ring is the square root of n times wavelength times the lens radius of curvature. Bright rings have a similar formula with a half integer shift. This elegant setup turns a simple lens into a Newton's rings can be used to measure the wavelength of monochromatic light very accurately. By measuring the diameters of two rings of orders n and n plus p, we can extract the wavelength using a simple formula involving these diameters and the radius of curvature. The same experiment can also measure the refractive index of a liquid placed between the lens and the plate. This makes Newton's rings. Let us summarize this section. Coherence combined with path difference produces observable interference. In Young's double-slit experiment, the fringe width is wavelength times screen distance divided by slit separation. Thin films owe their colors to the path difference relation and the additional half wavelength shift at reflection. Finally, Newton's rings show ring radii that grow as the square root of the order, making them ideal for precise wavelength and reflection. Typical exam questions on this topic include defining coherence and stating conditions for sustained interference. You should be able to derive the expression for fringe width in Young's experiment. Another popular question is explaining the colors in thin films using the path difference condition. Be prepared to describe Newton's rings experiment and derive the wavelength formula. Finally, you should distinguish Fresnel and Fraunhofer diffraction, which leads. We now turn to diffraction, the phenomenon where light bends around obstacles and reveals its wave nature in. Diffraction is the bending of light into the geometrical shadow of an obstacle, accompanied by a redistribution of intensity. There are two important regimes. In Fresnel diffraction, the source or screen is at a finite distance and the wavefronts are curved. In Fraunhofer diffraction, the source and screen are effectively at infinity with plane wavefronts, often achieved using lenses. Most engineering applications use the Fraunhofer regime because of its. Consider a single slit of width illuminated by monochromatic light. The intensity distribution on the screen follows a sinc-squared pattern. Minima appear where the slit width times the sine of the diffraction angle equals integer multiples of the wavelength. The width of the central maximum on the screen is inversely proportional to the slit width. This means that narrower slits produce wider diffraction patterns. A key. This graph shows the single slit intensity distribution. There is one tall central peak, flanked by progressively smaller side peaks. Most of the diffracted energy, about 84%, is concentrated in the central maximum. The side lobes carry less and less energy as we move outward. This pattern explains why beams of light spread out after passing through narrow apertures, and it sets a fundamental limit on the sharpness. Consider a single slit of width 0.1 mm illuminated by light of wavelength 600 nanometers. The first minimum occurs at a sine angle of 6 times 10 to the minus 3. Therefore, the angular full width of the central maximum is about 0.7 degrees or 12 milliradians. This shows how even a very small slit produces a measurable. The double slit pattern is actually a combination of single slit diffraction and to-source interference. The interference fringes from the two slits are modulated by the single slit diffraction envelope. Sometimes an interference maximum coincides exactly with a diffraction minimum, producing what we call a missing order. This happens when the slit separation divided by the slit width is an integer. Understanding this combined pattern is essential for analyzing. A diffraction grating consists of many equally spaced parallel slits. The intensity distribution involves the single slit envelope multiplied by an interference factor. Principal maxima occur where the grating element times the sine of the angle equals integer multiples of the wavelength. This is known as the grating equation. The resolving power of a grating is the order times the number of slits, while the dispersive power describes how an. Grating spectrometers have many engineering applications. They determine unknown wavelengths and identify materials by their atomic emission spectra. In optical communication, they enable wavelength division multiplexing, packing many channels into one fiber. In astronomy, they reveal the chemical composition of stars. Two close spectral lines are just barely resolved when the principal maximum of one falls on the first minimum of the other. This is. Diffraction limits the resolving power of every optical instrument. For a telescope with a circular aperture, the minimum resolvable angle is 1.22 times wavelength divided by aperture diameter. For a microscope, The smallest resolvable distance is 0.61 times wavelength divided by numerical aperture. This diffraction limit is a fundamental cap, although modern super-resolution techniques like STED, PALM, and STORM cleverly circumvent it. These advances have revolutionized. Let us summarize this section. For a single slit, minima occur where slit width times sine angle equals integer wavelengths with a sinc-squared envelope. Double slits and gratings combine interference with the single slit envelope. The grating equation underlies all of spectroscopy. Most importantly, diffraction sets a fundamental resolution limit. Typical exam questions on this topic include distinguishing Fresnel and Fraunhofer diffraction. You should be able to derive the intensity formula for single-slit Fraunhofer diffraction. Discuss missing orders in the double-slit pattern. Define the dispersive power and resolving power of a grating. Finally, state and derive the Rayleigh. We now move into the section on polarization, which reveals the transverse nature of light and provides the basis for many. Polarization refers to the orientation of the electric field vector in a transverse way. Light becomes polarized when its electric field oscillates along a specific direction. There are several types. Linear or plane polarization keeps the electric field in one direction. Circular polarization has the field rotating uniformly. Elliptical polarization is the general case. Unpolarized natural light has random orientation. Polarized light can be produced through several physical processes. Reflection at a particular angle, governed by Brewster's law, produces fully polarized reflected light. Refraction through birefringent crystals splits light into polarized components. Selective absorption in Polaroid sheets transmits only one polarization. Scattering in the atmosphere, such as Rayleigh scattering of sunlight, also polarizes light. Double refraction in calcite and quartz produces. Brewster's law states that at a specific angle of incidence, light reflected from a dielectric surface is completely linearly polarized. At this Brewster angle, the tangent of the angle equals the refractive index of the medium. Also, the reflected and refracted rays are perpendicular to each other. For ordinary glass with refractive index 1.5, the Brewster angle is about 56 degrees. This principle is used in polarizing sunglasses and in Brewster windows. Malus's law describes how linearly polarized light is reduced when it passes through an analyzer. If the analyzer's transmission axis makes an angle theta with the polarization direction, the transmitted intensity equals the incident intensity multiplied by cosine squared theta. This means that at 0 angle the full beam passes through, while at 90 degrees no light passes. Malus's law is the basis of every polarization analyzer used in laboratories. Crystals like calcite and quartz exhibit double refraction. An incoming ray splits into the ordinary ray, which obeys Snell's law, and the extraordinary ray, whose refractive index depends on direction. There is a special direction called the optic axis where the two indices coincide. By selecting the thickness, we can build wave plates. A quarter wave plate converts linear to circular polarization, while a half wave plate rotates the plane of polarization by 90 degrees. These are essential components in polarization. Has many engineering applications. Liquid crystal displays use polarization gates for every pixel. 3D cinema relies on orthogonal circular polarizations for the two eyes. Stress analysis in transparent components uses photoelasticity. Saccharimetry measures sugar concentration through optical rotation. Polarization: maintaining fibers preserve a specific polarization state over long distances in. Let us summarize this section. Polarization confirms the transverse nature of light. Brewster's law gives a tangent relation between Brewster angle and refractive index, while Malus's law gives the cosine squared dependence for intensity after an analyzer. Birefringence enables wave plates, which are the workhorses of polarization optics. Typical exam questions include proofs of Brewster and Malus's laws, and a description of double refraction. The next section is dedicated to lasers, one of the most transformative technologies of the 20th. The word laser stands for light amplification by stimulated emission of radiation. Between two atomic energy levels, three processes can occur. Stimulated absorption raises an atom from the lower to the upper level on absorbing a photon. Spontaneous emission drops an atom from the upper level with random phase and direction. Stimulated emission, the key to laser action, produces an identical coherent photon when an incoming photon triggers a downward transition. It is this coherent amplification that Einstein analyzed atom-photon interactions using three coefficients. B12 governs absorption, A21 governs spontaneous emission, and B21 governs stimulated emission. By requiring thermal equilibrium with blackbody radiation and using Planck's distribution, Einstein derived a beautiful relation showing that the ratio of A to B coefficients is proportional to frequency cube. This result links the discrete quantum picture of atoms with the continuous radiation field and gave a quantum mechanical. For laser action to occur, the upper energy level must contain more atoms than the lower one. This condition is called population inversion, and it is fundamentally non-thermal. Achieving inversion requires 3 or 4 level systems, since a simple two-level system cannot do it. A pumping mechanism, such as optical, electrical, or chemical pumping, supplies the energy. A metastable upper state with a long lifetime allows the inversion to build up. An optical resonator then provides feedback. A laser has three essential components. The active medium can be a gas, solid, liquid, or semiconductor where stimulated emission occurs. The pumping source supplies energy through a flash lamp, electric current, or radio frequency excitation. The optical resonator consists of two mirrors. One is a high reflectivity rear mirror, the other is a partially transmitting output coupler. Together these elements turn random spontaneous emission into a. Two important laser schemes are commonly used. In a three-level scheme, atoms are pumped from the ground state to a high level, then drop quickly to a metastable level. Lasing occurs back to the ground state. The ruby laser is a classic example. In a four-level scheme, the lower laser level is above the ground state and empties quickly. This makes inversion much easier to maintain. Neodymium YAG and helium neon lasers use this scheme. Four-level systems are generally more efficient. Laser light has four remarkable properties. It is highly monochromatic, with extreme spectral purity, far surpassing ordinary light sources. It is coherent, both spatially and temporally, making interference and holography possible. It is highly directional, with very small beam divergence. Finally, it has very high intensity and brightness. These properties make lasers indispensable in communication, medicine, manufacturing. The ruby laser was the first laser ever demonstrated. It uses a chromium-doped aluminum oxide rod as the active medium. A xenon flash lamp provides the optical pump. It emits at 694.3 nanometers in the red part of the spectrum. Operation is pulsed based on a 3-level scheme. Applications include ranging, holography recording, and tattoo removal. Its main limitations are low efficiency, around 1%. The helium-neon laser uses a gas mixture of helium and neon in a 10:1 ratio at low pressure. A DC electric discharge provides the pumping. The principal output is at 632.8 nanometers in the red, with additional lines in the infrared. Excited helium atoms transfer energy resonantly to neon, which then lasers through 4-level transitions. Operation is continuous wave with high coherence. Applications include interferometry, alignment, holography. A semiconductor or diode laser operates by stimulated emission across the band gap of a heavily doped p-n junction. The emission wavelength is set by the band gap energy. Gallium arsenide emits near 840 nanometers, while indium gallium arsenide phosphide emits at 1.55 micrometers for telecom. A threshold current must be exceeded to establish population inversion in the active region. Semiconductor lasers are compact, electrically pumped, and highly efficient, often more than 50%. They power optical communication, optical discs. Let us calculate how many photons a 1 milliwatt helium neon laser emits per second at 632.8 nanometers. Each photon carries an energy equal to Planck's constant times the speed of light divided by the wavelength, which works out to about 3.14 times 10 to the minus 19 joules. Dividing the laser's power by the photon energy gives roughly 3.2 times 10 to the 15 photons per second. Even a tiny laser pumps out an enormous number. Lasers find applications across virtually every engineering discipline. They cut, weld, drill, and mark in materials processing. They form the backbone of optical communication through fiber lasers and semiconductor lasers. In medicine, they enable LASIK, surgery, and photodynamic therapy. In defense, they support LIDAR, range finding, and target designation. They drive holography, ultra-precise metrology, and even fusion energy research at facilities like the Holography is a remarkable application of laser light. Unlike photography, which records only intensity, a hologram records both amplitude and phase of the light scattered by an object. An object beam interferes with a coherent reference beam on a film, producing a complex interference pattern. When illuminated again by the reference beam, the original three-dimensional wavefront re-emerges with full parallax. Applications include security holograms on currency, holographic data storage, head-up displays, holographic interferometry for vibration analysis. Let us summarize this section. Lasers require stimulated emission, population inversion, and an optical resonator. The Einstein coefficients established the quantum basis of stimulated emission. 3 and 4 level schemes need metastable upper states. Laser light is monochromatic, coherent, directional, and intense. Typical exam questions ask you to derive the Einstein relations, explain population inversion and pumping, describe the construction and working of major laser types, and list properties. We now move to fiber optics, the technology that carries the modern internet and underpins long-distance data. An optical fiber is a thin glass or plastic cylinder that guides light by repeated total internal reflection. Each fiber has a high refractive index core, typically about 50 micrometers across, surrounded by a cladding of lower index and protected by an outer jacket. Light entering the core is trapped by total internal reflection at the core cladding interface and propagates along the fiber for many kilometers. Total internal reflection requires that the angle inside the fiber exceeds the critical angle. The acceptance angle in air defines the cone of light that can be coupled into the fiber. It depends on the difference of refractive indices between core and cladding. The numerical aperture is defined as the sine of the acceptance angle and equals the square root of the index difference squared. A higher numerical aperture means more light gathering, but optical fibers are classified by their refractive index profile and number of guided modes. Step index single mode fibers carry only the fundamental mode and are used for long-haul telecom. Step index multi-mode fibers carry many modes and are used for shorter links and sensors. Graded index multi-mode fibers have a parabolic index profile that reduces modal dispersion. The V number, a dimensionless parameter, determines how many modes propagate. A V number below 2.405 ensures attenuation in a fiber is the power loss per unit length, expressed in decibels per kilometer. Modern silica fiber achieves about 0.2 decibels per kilometer at 1.55 micrometers. Loss sources include absorption by hydroxyl ions, Rayleigh scattering, and bending losses. Dispersion broadens pulses and limits data rates. It includes modal dispersion in multimode fibers, material dispersion due to wavelength-dependent refractive index, and waveguide dispersion from. Consider a step index fiber with core index 1.5 and cladding index 1.48. The numerical aperture works out to about 0.244. The corresponding acceptance angle is roughly 14 degrees. This means only light entering the fiber within a 14-degree cone will be guided. Light outside this cone simply leaks into. An optical fiber communication system has several stages. Information is encoded and modulated, then converted into light by a laser or LED. The light travels through the fiber to the receiver, where a photodetector converts it back into electrical signals. The signals are then demodulated and decoded to recover the original information. Compared to copper, fibers offer enormous bandwidth, very low loss, immunity to electromagnetic interference. Fiber optics has many applications. Long-haul and undersea cables form the global telecommunication backbone. Fiber to the home delivers broadband internet to households. In medicine, fibers enable endoscopy and minimally invasive surgery. Fiber Bragg grating sensors monitor temperature, strain, and pressure in industrial systems. Erbium-doped fiber amplifiers boost signals over long distances. Defense and aerospace systems also rely heavily on fiber-based. Let us summarize this section. Light is guided by total internal reflection in the high index core. Numerical aperture and V number characterize light gathering and modal behavior. Single-mode fiber operating at 1.55 micrometers is the workhorse of modern telecom, with extremely low loss. Typical exam questions cover the derivation of acceptance angle and numerical aperture, classification of fibers, attenuation and dispersion, and the block diagram of a fiber. We now enter one of the most exciting parts of the course, the origins of quantum mechanics. This section will introduce the experiments and ideas that shattered classical physics. By 1900, several experiments could not be explained by classical wave or particle theory. These included the blackbody radiation spectrum with its ultraviolet catastrophe, the photoelectric effect, Compton scattering, atomic emission line spectra, and the specific heats of solids at low temperatures. Each of these puzzles called for a radical new framework. Their resolution gave Max Planck proposed that the energy of an oscillator is quantized in discrete units of h-nu. This bold idea led to his radiation law, which correctly describes the spectrum of a blackbody. At low frequencies, Planck's law reduces to the classical Rayleigh-Jeans law, while at high frequencies it agrees with Wien's law. It also yields the Stefan Boltzmann law for total radiated power. Planck's hypothesis was the first crack in. Einstein extended Planck's idea by treating light itself as a stream of quanta called photons. When a photon of energy h-nu hits a metal surface, it can eject an electron. Einstein's photoelectric equation states that the photon energy equals the work function plus the maximum kinetic energy of the ejected electron. Below a threshold frequency, no electrons appear, no matter how intense the light. The stopping potential and the linear relation between photon energy and electron kinetic energy confirmed the particle picture of light. This work earned Compton scattering provided further direct evidence for the photon picture. When an X-ray photon scatters off a free electron, its wavelength increases by an amount that depends on the scattering angle. The shift involves the Compton wavelength of the electron, about 2.43 picometers. This result establishes that the photon is a relativistic particle with energy h-nu and momentum h-nu over c. It marked the final acceptance of light as Louis de Broglie proposed that every particle has a wave associated with it, with wavelength equal to Planck's constant divided by momentum. For an electron accelerated through 100 volts, the de Broglie wavelength is about 1.23 angstroms, comparable to atomic spacings in crystals. This suggested that electron beams could be diffracted by crystals just like X-rays. Davison and Germus' experiment in 1927 beautifully Davison and Germus scattered low-energy electrons from a nickel single crystal and observed a sharp diffraction peak at 50 degrees. Using de Broglie's relation, the predicted wavelength matched the Bragg analysis of the nickel crystal extremely well. This was direct evidence for electron waves. G. P. Thomson independently observed electron diffraction through thin metal foils the same year. Both shared the Nobel Prize in 1937 for confirming the Heisenberg's uncertainty principle states that conjugate variables, such as position and momentum, or energy and time, cannot both be measured to arbitrary precision simultaneously. The product of their uncertainties is bounded by approximately h bar over 2. This principle can be understood from the wave packet picture. An important consequence is that a confined particle must possess a minimum non-zero energy, known as the zero-point energy. This rules out the classical idea of perfectly still particles. Suppose an electron is confined within a region of about 1 angstrom. By the uncertainty principle, the minimum momentum uncertainty is about 5 times 10 to the minus 25 kilogram meters per second. Substituting this into the kinetic energy formula gives a minimum energy of roughly 0.95 electron volts. This is the energy scale for electrons in atoms, and helps explain atomic sizes and a quantum particle is described by a complex wave function psi. According to Bohr's interpretation, the squared modulus of psi gives the probability density of finding the particle at a given location. The wave function must be normalized so that the total probability is 1. Physical conditions also require psi to be single-valued, finite, continuous, and to have a continuous first derivative wherever the potential is finite. These conditions ensure that probabilities. In quantum mechanics, every physical observable is associated with a Hermitian operator. Position is represented by multiplication, momentum by a derivative operator, and energy by the Hamiltonian operator, which includes kinetic and potential energy terms. The expectation value of an observable is obtained by sandwiching its operator between psi star and psi and integrating. This rule replaces the classical notion of a definite measurement value. We now reach the central equation of quantum mechanics, the Schrödinger equation, which governs how wave functions. For a non-relativistic particle of mass m in a potential v, the time-dependent Schrödinger equation relates the time derivative of psi to a spatial operator involving the Laplacian and the potential. It is a linear partial differential equation, first order in time. As a check, for a free particle plane wave, the equation reproduces the correct de Broglie relation between energy and momentum. This equation is the quantum mechanical analog. When the potential depends only on position, we can separate the time and space dependence in psi. This yields the time-independent Schrödinger equation, an eigenvalue equation for energy. The energy eigenvalues label the allowed stationary states of the system. In a stationary state, the wave function picks up only a global phase factor with time, so the probability density remains constant. This separation is the starting point for solving most bound state problems. Just as charge satisfies a continuity equation in electromagnetism, probability satisfies one in quantum mechanics. The probability current involves the gradient of psi and its complex conjugate. Together with the time evolution of psi squared, this gives a continuity equation expressing local conservation of probability. Probability never appears or disappears. It can only flow. This idea is crucial for understanding tunneling currents, such as those exploited in quantum mechanics. Rests on 6 postulates. The state of a system is described by a vector in a Hilbert space. Every observable corresponds to a Hermitian operator. The only possible measurement outcomes are the eigenvalues of that operator. The probability of obtaining a particular eigenvalue is given by the squared overlap of psi with the corresponding eigenstate. After measurement, the wave function collapses onto that eigenstate. Between measurements, the system evolves accordingly. Let us summarize the quantum foundations. Quantization emerged from the work of Planck, Einstein, Compton, and de Broglie. The uncertainty principle is intrinsic to wave packets. The wave function carries all information about a system, with its squared modulus representing probability density. The time-independent Schrödinger equation is the eigenvalue equation for energy of a stationary state. Common exam questions cover Planck's law, the photoelectric effect, de Broglie wavelength, and derivation of the time-independent. Our next section is the particle in a box, a foundational quantum mechanics problem that illustrates quantization. Consider a particle confined to a one-dimensional box of width L. Inside the box the potential is 0, while outside it is infinite. The time-independent Schrödinger equation inside the box reduces to a simple second-order differential equation. Because the potential is infinite outside, the wave function must vanish at both walls. These boundary conditions select only certain allowed wave. The allowed wave functions in a box are sine functions that vanish at both walls. energies are quantized and grow as the square of the integer quantum number n. Key features include quantized energies proportional to n squared, a non-zero zero-point energy for the ground state, and an increasing number of nodes as n grows. The energy spacings widen as the box shrinks. This effect, called quantum confinement, is central. This diagram shows the first four wave functions of a particle in a box. The ground state has no node inside the box. The first excited state has one node. The second excited state has two nodes, and so on. Each higher state has one more node than the one below. This nodal structure is a universal feature of bound quantum states and helps us visualize them. Consider an electron confined in a one-dimensional box of width 1 nanometer. The ground state energy works out to roughly 6 times 10 to the minus 20 joules, or about 0.38 electron volts. The third level, with n equal to 3, is 9 times higher, around 3.4 electron volts. These values fall in the range of typical atomic energies, showing why nanoscale electronic devices in 3 dimensions, a cubical box of side L gives rise to wave functions that are products of 3 one-dimensional sine functions. The energy depends on 3 quantum numbers, one for each axis. Because the energies depend on the sum of the squares of the quantum numbers, different combinations can give the same energy. This is called degeneracy. Degeneracy plays a central role in atomic structure and in the optical properties. Quantum dots are real-life realizations of 3-dimensional boxes for electrons. Their emission wavelengths are tunable by changing the dot size. Quantum wells, wires, and dots correspond to confinement in 1, 2, and 3 directions, creating 2D, 1D, and 0D electron gases. These structures are used in quantum dot LEDs, semiconductor lasers, single photon sources, and advanced photovoltaics. Common exam questions include solving the 1D infinite well, discussing reflection and degeneracy, and finding the most probable position of a particle. We now study free electron theory and band theory, which together explain how electrons behave inside solids and why some materials conduct. The Drude model treats the valence electrons in a metal as a gas of free charged particles that move through the lattice and occasionally collide with positive ions. A characteristic relaxation time describes the average interval between collisions. In equilibrium, the electrons obey Maxwell-Boltzmann statistics. This model gives the famous formula for electrical conductivity in terms of carrier density, charge, and relaxation time. It also predicts the Weidmann-Franz law connecting thermal and. The Drude model has several drawbacks. It predicts a large electronic contribution to specific heat that is not observed experimentally. It gives the wrong temperature dependence of resistivity and paramagnetism. It also fails to explain why some solids are insulators and others semiconductors. The resolution requires treating electrons quantum mechanically using Fermi-Dirac statistics. This more refined picture leads naturally to the Sommerfeld treated electrons in a metal as non-interacting fermions filling allowed states up to the Fermi energy. The density of states for a 3-dimensional electron gas grows as the square root of energy. Integrating up to the Fermi energy gives the carrier density, and the Fermi energy depends on this density to the 2/3 power. At finite temperature, electrons obey the Fermi-Dirac distribution, which smoothly cuts off at the Fermi level. The Sommerfeld model achieves several important successes. It predicts the correct temperature linear electronic specific heat at low temperatures. It explains polyparamagnetism in metals. It also recovers the Weidmann-Franz law with the correct value of the Lorentz constant. However, it still ignores the effect of the periodic ion lattice on electron motion. This last omission leads us to band theory, which explains the difference between metals, semiconductors. Inside a crystal, electrons move in a periodic potential, repeating with the lattice. Bloch's theorem states that the eigenfunctions in such a potential can be written as plane waves modulated by a periodic function. As a consequence, the allowed electron energies form continuous bands separated by forbidden gaps. This is the fundamental result of band theory, and it explains qualitatively why some materials conduct. The Kronig-Penney model is a one-dimensional periodic square well potential that can be solved exactly. The allowed energies satisfy a transcendental condition involving a parameter that measures the strength of the periodic potential. The model shows that forbidden energy gaps open at the boundaries of the Brillouin zone. In the limit of weak potential, the energy reduces to the free electron parabola. In the limit of strong potential, the spectrum approaches discrete atomic levels. Real crystals. Inside a band, electrons respond to forces as if they had a modified mass called the effective mass. It is defined by the curvature of the energy versus wave vector curve. Near a band minimum, the effective mass is positive and the carriers behave like ordinary electrons. Near a band maximum, the effective mass becomes negative, and we describe these carriers as holes with positive mass. The effective mass controls mobility, density of states, and solids can be classified by their band filling. In a conductor, valence and conduction bands overlap or the highest band is partially filled. In a semiconductor, a small energy gap of about 1 electron volt separates a filled valence band from an empty conduction band. In an insulator, the gap is much larger, typically more than 5 electron volts. This simple band picture explains the enormous range of electrical conductivity. Let us summarize this section. The periodic potential of a crystal turns continuous energy spectra into bands separated by forbidden gaps. Bloch's theorem and the Kronig-Penney model capture the essential physics. The effective mass and band filling together decide whether a solid behaves as a metal, semiconductor, or insulator. Common exam questions ask you to compare classical, Sommerfeld, and band theories, derive Fermi energy, state Bloch's theorem. Our next section is Semiconductor Physics, the foundation of all modern electronics. This is where the abstract concepts of band theory meet practice. An intrinsic semiconductor is a pure crystalline material with no added impurities. Its carrier concentration depends entirely on thermal excitation of electrons across the band gap. The intrinsic carrier density at temperature T depends exponentially on minus the band gap divided by twice kBT, multiplied by an effective density of states factor. This sensitive dependence on temperature is a defining feature. In an intrinsic semiconductor at absolute zero, the Fermi level lies exactly midway in the band gap. At finite temperature, it shifts slightly due to the difference in effective masses of electrons and holes. The conductivity is a sum of electron and hole contributions, with equal carrier densities since each thermally excited electron leaves behind a hole. Typical band gaps are 1.12 electron volts for silicon, 0.67 for germanium, and 1.43 for gallium arsenide. These differences shape. Doping introduces controlled impurities to greatly increase carrier density. Pentavalent dopants like phosphorus, arsenic, or antimony donate extra electrons, creating an N-type semiconductor. Trivalent dopants like boron, aluminium, gallium, or indium create holes, producing P-type material. The law of mass action states that the product of electron and hole concentrations equals the square of the intrinsic carrier density, regardless of doping. This simple rule governs all. In N-type material with fully ionized donors, the electron concentration is approximately the donor density, while the hole concentration is much smaller. In P-type material, the situation is reversed. The Fermi level moves towards the conduction band in N-type material and towards the valence band in P-type. These shifts of the Fermi level are central to understanding all carriers in semiconductors move by two main mechanisms. Drift is the motion in response to an electric field, with current density proportional to mobility and carrier density. Diffusion is the motion due to a concentration gradient, with current proportional to the gradient. The Einstein relation connects the diffusion coefficient and mobility through the thermal voltage kBT over E. Together, drift and diffusion explain how currents flow in. When a current-carrying conductor sits in a transverse magnetic field, a voltage develops perpendicular to both the current and the field. This is the Hall effect, and the resulting voltage depends on current, magnetic field, carrier density, and sample thickness. The Hall coefficient is the inverse of charge density. The sign of the Hall coefficient tells us whether the carriers are electrons or holes. Its magnitude gives the carrier density, and combined with conductivity, consider a semiconductor with a Hall voltage of 6.25 mV at a current of 10 milliamperes, a magnetic field of half a Tesla, and thickness 1 mm. The Hall coefficient works out to about 1.25 times 10 to the minus 3 cubic meters per coulomb. Dividing by the elementary charge gives a carrier density of 5 times 10 to the 21 per cubic meter. This kind of measurement is routinely used to characterize. At a p-n junction, holes diffuse from p to n side and electrons diffuse from n to p side. This leaves behind a region of charged dopant ions called the depletion region. An internal electric field builds up that opposes further diffusion, eventually reaching equilibrium. The built-in potential depends logarithmically on the doping levels relative to the intrinsic carrier density. This depletion region is the heart of all. The ideal Shockley diode equation describes the current-voltage relation of a p-n junction. In forward bias, the current grows exponentially with applied voltage. In reverse bias, only a tiny saturation current flows. The graph shows this asymmetric behavior clearly. This rectifying property is the foundation of diodes, and through extension, of every transistor. At sufficiently high reverse voltages, a p-n junction breaks down. In Zener breakdown, heavy doping and a narrow depletion region cause field-induced tunneling at voltages below about 5 volts, with a negative temperature coefficient. In avalanche breakdown, lightly doped junctions experience impact ionization at high fields, with a positive temperature coefficient. Both produce a nearly constant reverse voltage, which is the basis of Zener voltage regulators. Let us summarize this section. Intrinsic carrier density depends exponentially on the band gap. Doping shifts the Fermi level and dramatically increases carrier density. Drift, diffusion, and recombination together govern device operation. The Hall effect identifies the carrier type, and the p-n junction forms the foundation of solid-state electronics. Common exam questions include deriving expressions for intrinsic carrier density and Fermi level, the law of mass action, the Einstein relation, the Hall effect. We now move to diodes and transistors, the workhorses of all modern electronics. Every smartphone, computer, and communication system relies. There are many specialized diodes. The rectifier diode is used in power conversion. The Zener diode regulates voltage. The light-emitting diode produces light through electroluminescence. The photodiode detects light when reverse biased. The solar cell harvests photogenerated carriers. The Schottky diode uses a metal semiconductor junction for fast switching. The tunnel diode shows a negative resistance region, and the varactor provides voltage. Rectifiers convert AC to DC. A half-wave rectifier uses one diode, has an output of Vm over pi, an efficiency of about 40%, and high ripple. A full-wave bridge rectifier uses 4 diodes, doubles the output, raises efficiency to about 80%, and reduces ripple. Filters such as capacitors, inductors, or pi-section LC networks smooth the output further. These circuits form the front end of a bipolar junction transistor consists of two back-to-back p-n junctions in either NPN or PNP configuration. Its operation depends on biasing. In active mode, the emitter base junction is forward biased and the collector base junction is reverse biased. In cutoff, both junctions are reverse biased, and in saturation both are forward biased. The current relation states that emitter current equals base current plus collector current, with the current gains alpha and beta. A BJT can be wired in 3 configurations: common base, common emitter, and common collector. Each has distinct input and output impedances, voltage and current gains, and phase characteristics. Common base has low input and high output impedance, suitable for radio frequency amplification. Common emitter is the general-purpose amplifier with 180-degree phase inversion. Common collector or emitter follower acts as a buffer with very high input impedance. Field effect transistors are voltage-controlled devices. The junction FET has a reverse-biased gate and offers extremely high input impedance. The MOSFET has an oxide-isolated gate and comes in enhancement or depletion mode, N-channel or P-channel. The drain current in saturation is a quadratic function of the gate voltage minus the threshold voltage. MOSFETs are the building blocks of modern digital electronics, especially in complementary MOS. Diodes and transistors have countless engineering applications. They form power supplies, rectifiers, and voltage regulators. They build amplifiers for audio, radio frequency, and low-noise systems. They drive oscillators, mixers, and modulators. They implement digital logic gates and microprocessors. They act as switches in power electronics, using insulated gate bipolar transistors and MOSFETs. Finally, LEDs and laser diodes power lighting and displays, while solar cells harvest. Let us summarize this section. Diodes exploit the asymmetric p-n junction for rectification, detection, and regulation. Bipolar transistors are current-controlled, while field effect transistors are voltage-controlled. Both serve as amplifiers and switches. CMOS technology underpins all modern computing. Typical exam questions include deriving efficiency and ripple factor of rectifiers, comparing BJT configurations, deriving drain current of a MOSFET, and we now study superconductivity, a remarkable quantum phenomenon where materials lose all electrical resistance and exclude magnetic fields. Superconductivity was discovered in 1911 by Kamerlingh Once, who observed that mercury loses all electrical resistance below 4.2 Kelvin. A superconductor is a material that shows zero electrical resistance below a critical temperature and also expels magnetic flux from its interior. This expulsion is called the Meissner effect, and it distinguishes a true superconductor from high. Three quantities characterize the superconducting state. The critical temperature is the highest temperature at which superconductivity occurs. The critical magnetic field destroys superconductivity above a certain value, and it falls parabolically with temperature. The critical current density is the maximum current density a superconductor can carry without losing its superconducting state. Together these define the operating envelope for superconductors. Come in two types. Type 1 superconductors have a single critical magnetic field and no mixed state. Pure metals like mercury, lead, and tin are type 1 and are mainly of historical interest. Type 2 superconductors have two critical fields, with a mixed state of flux vortices between them. Alloys such as niobium titanium and niobium 3 tin, as well as high-temperature superconductors like yttrium barium copper oxide, are type 2. These are the materials used in MRI magnets. The microscopic theory of superconductivity was developed by Bardeen, Cooper, and Schrieffer in 1957. An attractive interaction between electrons, mediated by lattice vibrations called phonons, leads to the formation of Cooper pairs. These pairs of electrons with opposite momenta and spins condense into a single coherent quantum state with an energy gap. Breaking a pair requires at least the gap energy, and this minimum cost is why supercurrents flow without resistance. BCS theory predicts a universal relation linking the London equations describe the electrodynamics of superconductors. Combined with Maxwell's equations, they predict that magnetic fields decay exponentially inside a superconductor. The characteristic length scale is called the London penetration depth, and it depends on the density of superconducting carriers. This sets the depth to which a magnetic field penetrates before falling to 1 over E of its surface value, and it is a key parameter in When two superconductors are separated by a thin insulating barrier, Cooper pairs can tunnel between them. The DC-Josephson effect produces a supercurrent even at zero applied voltage. The AC-Josephson effect produces an oscillating current under a constant voltage, with frequency proportional to that voltage. These effects power superconducting quantum interference devices or SQUIDs, the most sensitive magnetometers known. They also underlie voltage standards and the qubits used in superconductors have a wide range of engineering applications. They form the magnets in MRI scanners and particle accelerators such as the Large Hadron Collider. They lift maglev trains in Japan and China. They serve as fault current limiters and high-capacity power cables. SQUID magnetometers are used in geology, biomagnetism, and mineral exploration. Superconducting transmon qubits are also at the heart of leading. Let us summarize this section. Zero resistance combined with the Meissner effect defines a superconductor. Type 1 materials have a single critical field, while Type 2 materials show a mixed state between two critical fields. BCS theory explains superconductivity through phonon-mediated Cooper pairs with a universal gap relation. Josephson effects underpin SQUIDs and qubits. Typical exam questions ask you to state properties, distinguish types, explain the Meissner effect, describe BCS theory, and discuss. The next section is on nanotechnology, the design and use of structures at the scale where quantum and nanotechnology is the design, characterization, production, and application of structures, devices, and systems with dimensions between 1 and 100 nanometers. These sizes matter because several physical effects become dominant. Quantum confinement modifies electronic properties. The surface-to-volume ratio greatly enhances chemical activity. Mean free path effects govern transport. Optical resonances called plasmons appear at characteristic sizes, giving nanomaterials a nanostructures are classified by the number of dimensions in which they are confined. Bulk materials are confined in 0 directions and are 3-dimensional. Thin films and quantum wells are confined in 1 direction, giving 2-dimensional electron systems. Nanowires and quantum wires are confined in 2 directions, giving 1-dimensional systems. Quantum dots are confined in all 3 directions, behaving as 0-dimensional artificial atoms. Each class has distinctive electronic. There are 2 complementary routes to nanomaterials. Top-down approaches start with bulk material and carve it down to the nanoscale using lithography, etching, or ball milling. Photolithography, electron beam lithography, and extreme ultraviolet lithography are key technologies in this category. Bottom-up approaches assemble nanostructures atom by atom or molecule by molecule. Methods include chemical and physical vapor deposition, molecular beam epitaxy, atomic layer deposition, sol-gel processing, self-assembly. Characterizing nanomaterials requires a battery of techniques. Scanning and transmission electron microscopes reveal morphology and crystallography. Atomic force and scanning tunneling microscopes give surface topography down to atomic resolution. X-ray diffraction identifies crystal structure and phase. Raman and infrared spectroscopy provide vibrational fingerprints. Ultraviolet visible and photoluminescence spectroscopy probe optical band gaps. X-ray photoelectron spectroscopy gives elemental and chemical state information. And BET analysis measures. Several nanomaterials stand out for their unique properties. Carbon nanotubes are rolled graphene sheets with ballistic electron transport and Young's modulus on the terapascal scale. Graphene itself is a single atomic layer of carbon with massless Dirac fermions and extraordinary conductivity. Quantum dots show size-tunable photoluminescence used in QLED displays and biological imaging. Nano-silver and nano-gold exhibit plasmonic absorption useful for sensing and antibacterial coatings. Titanium dioxide and zinc oxide nanoparticles serve as photocatalysts. Nanotechnology enables many engineering breakthroughs. In electronics, it underlies sub-10 nanometer CMOS, FinFETs, and tunnel FETs. In photonics, it powers quantum dot LEDs, plasmonic devices, and metasurfaces. In energy, it provides high-capacity lithium-ion anodes, dye-sensitized solar cells, and fuel cells. In biomedicine, it enables targeted drug delivery, contrast agents, and biosensors. It strengthens composites and supports water purification and photocatalytic. Let us summarize this section. Properties at the nanoscale differ from bulk because of quantum confinement and surface effects. Top-down and bottom-up synthesis methods are complementary. Characterization spans electron microscopy, scanning probe techniques, diffraction, and spectroscopy. Typical exam questions ask you to define and classify nanomaterials, compare top-down and bottom-up approaches, discuss carbon nanotubes, and mention 3 applications of nanotubes. We now turn to electromagnetism, the unified theory of electric and magnetic phenomena. This subject underlies almost every electrical and electron. Vector calculus is the mathematical language of electromagnetism. The gradient gives the direction of steepest rise of a scalar field. The divergence measures the local source density of a vector field. The curl measures its rotational tendency. The Laplacian is the divergence of the gradient. Two integral theorems link these operators. Gauss's theorem connects a surface integral to a volume integral, and Stokes' theorem connects a line integral. Coulomb's law gives the force between two-point charges as proportional to the product of charges over the square of the distance. Integrating over a charge distribution gives the total electric field. Gauss's law states that the electric flux through any closed surface equals the enclosed charge divided by the vacuum permittivity. Equivalently, in differential form, the divergence of the electric field equals the charge density over epsilon 0. This is one of the electric field can be derived from a scalar potential by taking its negative gradient. The potential due to a charge distribution is an integral over the charge density divided by distance. The energy stored in an electrostatic configuration can be expressed either through charges and potentials, or as a volume integral of the electric field squared. Capacitance, defined as charge divided by voltage, characterizes any conductor pair. For a parallel plate capacitor, capacitance is proportional to area and inversely proportional. The Biot-Savart law gives the magnetic field of a current element as a cross product divided by distance squared. Ampere's law states that the line integral of the magnetic field around a closed loop equals the enclosed current times mu0. In differential form, the curl of the magnetic field equals mu0 times the current density. The Lorentz force on a moving charge combines the electric and magnetic contributions and is the basis of all charged. Faraday's law states that an electromotive force is induced whenever the magnetic flux through a circuit changes. The induced EMF equals the negative time derivative of the flux. Lenz's law captures the sign, the induced current opposes the change that produced it. Self-inductance describes the back EMF in a single coil, with stored energy proportional to current square. Mutual inductance couples to circuits and is the basis of transformers. These laws together underpin generators, motors. Electromagnetism powers a vast range of engineering systems. Generators and motors convert between electrical and mechanical energy. Transformers and power transmission lines distribute electrical energy efficiently. AC circuits and impedance matching are the foundation of electronics. Antennas and wireless propagation enable communication. Microwave engineering uses waveguides, klystrons, and magnetrons for high-frequency applications. Electromagnetic compatibility addresses interference issues in a series RLC circuit driven by a sinusoidal source obeys a differential equation involving the resistance, inductance, and capacitance. Its impedance combines resistive and reactive parts, and the phase angle between current and voltage depends on the imbalance between inductive and capacitive reactance. At a special resonance frequency, equal to 1 over square root of LC, the reactances cancel. The impedance is purely resistive and the current is maximum and in phase with the source. The quality factor measures the sharpness of resonance, and the bandwidth is the resonance frequency divided by Q. Engineering uses include radio tuning, filters, induction heating, MRI calls. Let us summarize this section. Static electromagnetism is governed by Coulomb's, Gauss's, Biot-Savart, and Ampere's laws. Dynamic effects bring in Faraday's law, paving the way to Maxwell's equations. Energy is stored in capacitors as half CV squared and in inductors as half Li squared. Common exam questions ask you to state and prove Gauss's law, derive the magnetic field of a long straight current, define self and mutual inductance, and express energy density. Our next section unifies electricity and magnetism through Maxwell's equations and shows that light itself. Ampere's law as originally formulated fails for a charging capacitor because no real current flows between the plates, yet a magnetic field clearly exists around the changing electric field. Maxwell repaired this by adding a new term called the displacement current density, equal to epsilon 0 times the time derivative of the electric field. This brilliant addition made the laws of electromagnetism consistent and predictable. Maxwell's four equations in vacuum are as follows. Gauss's law for the electric field relates field divergence to charge density. Gauss's law for the magnetic field states there are no magnetic monopoles. Faraday's law links the curl of the electric field to the time variation of the magnetic field. The Ampere-Maxwell law links the curl of the magnetic field to current density and the time variation of the electric field. Together they describe all classical in free space, taking the curl of Faraday's law and using the other Maxwell equations yields a wave equation. The electric field satisfies a wave equation whose speed equals 1 over the square root of mu 0 epsilon 0. This expression evaluates to the speed of light. An identical equation holds for the magnetic field. Maxwell concluded that light is an electromagnetic wave, unifying optics and electromagnetism. A plane electromagnetic wave can be written as a cosine function in space and time for both the electric and magnetic fields. Several important properties follow. The wave is transverse, with the electric field, magnetic field, and direction of propagation mutually perpendicular. Electric and magnetic fields are in phase, with the electric field equal to c times the magnetic field. The energy density is the sum of electric and magnetic contributions, and the Poynting vector gives the direction and the electromagnetic spectrum covers an enormous range of wavelengths. Radio waves above 1 meter are used for broadcasting and mobile communication. Microwaves from 1 millimeter to 1 meter drive radar and microwave heating. Infrared serves remote sensing and thermal imaging. Visible light spans roughly 400 to 700 nanometers. Ultraviolet enables sterilization and lithography. X-rays are used for imaging and crystallography, and gamma rays. Let us summarize this section. The displacement current completes Maxwell's equations. Electromagnetic waves are transverse, with speed equal to 1 over the square root of mu 0 epsilon 0. The Poynting vector quantifies energy flow. Typical exam questions include stating Maxwell's equations and explaining their physical meaning, deriving the wave equation from them, defining the Poynting vector with average intensity, and discussing engineering applications of. The next section is the special theory of relativity, Einstein's profound revision of space and time that revealed how mass, energy. Special relativity rests on two postulates. First, the laws of physics are the same in every inertial frame. Second, the speed of light in vacuum is the same in all inertial frames, regardless of the motion of the source. These simple statements have profound consequences. Simultaneity becomes relative, lengths contract, times dilate, and mass and energy turn out to be equivalent. These effects, though tiny at everyday speeds, are essential. Classical Galilean transformations work fine in Newtonian mechanics but conflict with Maxwell's equations. Einstein replaced them with Lorentz transformations. These mix space and time coordinates through a factor called gamma, which depends on the velocity v relative to c. Maxwell's equations are invariant under Lorentz transformations, showing that relativity and electromagnetism are deeply consistent. The Lorentz transformations form the geometric backbone Two famous consequences of special relativity are time dilation and length contraction. A moving clock ticks more slowly by a factor of gamma. A moving rod along its motion is shorter by the same factor. For example, muons created in the upper atmosphere at 0.99 times the speed of light have a Lorentz factor of about 7. Their effective lifetime in the lab frame becomes about 15 microseconds, explaining how they reach. When velocities are added in special relativity, the result is not simply the sum, as in Galilean physics. Instead, the resultant velocity is the sum divided by 1 plus the product of the two velocities over c squared. If two photons travel towards each other, this formula gives a relative velocity of c, not to c. No velocity ever exceeds the speed of light, which preserves the second postulate. In relativity, the mass of a moving object increases with velocity by the factor gamma. Momentum is mass times velocity with this same gamma factor. The total energy is gamma times the rest energy. The rest energy m0 c squared is intrinsic to the mass itself. Kinetic energy is the difference between total and rest energy. A famous relation links energy and momentum. Energy squared equals momentum times c squared. Consider a proton moving at 0.8 times the speed of light. Its Lorentz factor is about 1.667. The kinetic energy is the difference between total and rest energy, giving approximately 626 mega-electron volts. The total energy is around 1564 mega-electron volts. These are typical energies in particle accelerators and demonstrate how kinetic energy grows rapidly. Special relativity is naturally expressed in terms of 4 vectors. The 4 position combines time and space into a single object. The 4 velocity has gamma times c and gamma times the velocity vector as its components. The 4 momentum combines energy and 3 momentum with an invariant magnitude equal to mass times c. This elegant formalism unifies energy and momentum, mass and energy, and makes Lorentz. Special relativity has been confirmed by many experiments. The Michelson-Morley experiment yielded a null result that supported the constancy of the speed of light. Atomic clocks flown on aircraft, known as the Hafele-Keating experiment, measured time dilation directly. Cosmic ray muons and muons in storage rings show clear lifetime dilation. Mass-energy equivalence is verified daily in nuclear fission and fusion. GPS satellites require relativistic clock corrections to. Special relativity has many engineering applications. Particle accelerators including synchrotrons and colliders rely on relativistic dynamics. GPS positioning systems include relativistic clock corrections. Nuclear power and weapons exploit mass-energy equivalence through binding energy. Mass spectrometers and high-voltage electron microscopes operate at relativistic energies. Cosmic ray detectors and high-energy astrophysics instruments are also designed using. Let us summarize this section. 2 postulates lead to the Lorentz transformations. Moving clocks dilate, moving rods contract, and mass grows with gamma. The energy-momentum relation unifies these into one elegant formula. Common exam questions include stating the postulates and deriving the Lorentz transformations, deriving time dilation and length contraction, discussing the mass-energy relation, and describing three. We now move to crystal structure and X-ray diffraction, the foundation of materials science and the gateway to understand. Solids are broadly classified into three types. Crystalline solids have long-range periodic order, sharp melting points, and anisotropic properties. Examples include sodium chloride, quartz, and metals. Amorphous solids have only short-range order, soften gradually, and behave isotropically. Glass and many polymers fall into this category. Polycrystalline materials consist of many small crystallites and represent most engineering. A lattice is an infinite array of points generated by integer combinations of three primitive translation vectors. A basis is the group of atoms or molecules placed at every lattice site. A crystal is the combination of a lattice and a basis. A unit cell is the smallest portion of the crystal that, when repeated by translation, fills the entire structure. This simple framework lets us describe any crystal. There are 7 distinct crystal systems based on the relations between cell parameters. These are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. Within these systems there are 14 Bravais lattices distinguished by centering. For example, the cubic system has 3 Bravais lattices, simple, body-centered, and face-centered. These 14 Bravais lattices together describe every possible periodic. The most common cubic structures have different packing efficiencies. Simple cubic has 1 atom per cell, coordination 6, and a packing fraction of 0.52. Body-centered cubic has 2 atoms per cell, coordination 8, and packing fraction 0.68, and includes iron and chromium. Face-centered cubic has 4 atoms per cell, coordination 12, packing fraction 0.74, with examples like copper, aluminium, and nickel. Diamond structure has 8 atoms per cell, and an open packing of 0.34, found in carbon. Miller indices identify crystal planes systematically. Find the intercepts of a plane on the 3 axes in units of lattice constants. Take their reciprocals, then reduce to the smallest integer triplet. These 3 integers h, k, and l label the plane. For cubic crystals, the interplanar spacing is given by the lattice constant divided by the square root of h squared plus k squared plus l squared. This indexing system is essential for. The reciprocal lattice is built from primitive vectors related to the direct lattice through cross products. A reciprocal lattice vector is perpendicular to the corresponding family of planes and has magnitude inversely proportional to their spacing. The Brillouin zone is the Wigner-Seitz cell of the reciprocal lattice. This concept is central to electron band structure, phonon physics, and the analysis. Bragg's law states that constructive interference of X-rays reflected from successive crystal planes occurs when twice the interplanar spacing times the sine of the glancing angle equals an integer multiple of the wavelength. Because X-ray wavelengths are comparable to interatomic spacings, crystals act as 3-dimensional diffraction gratings. Measuring the angles at which diffraction occurs gives direct information about the spacing and arrangement. Several X-ray diffraction methods are used in practice. The law method uses white X-rays on a single crystal and produces a spot pattern used for orientation analysis. The powder method, often called Debye-Skurrer, uses monochromatic X-rays on powdered samples and produces concentric rings used for phase identification. The rotating crystal method spins a single crystal about an axis and gives three-dimensional structural information. Modern XRD instruments use CCD or CMOS detectors and Rietveld refinement. Consider copper K-alpha X-rays of 1.54 angstroms diffracting from the 100 planes of sodium chloride with a lattice constant of 5.64 angstroms. The interplanar spacing equals the lattice constant. Using Bragg's law, the sine of the first-order angle is about 0.136. The corresponding Bragg angle is approximately 7.85 degrees. This worked example shows how angels are. Real crystals always contain defects, which strongly influence properties. Point defects include vacancies, interstitials, and substitutional atoms, with named varieties like Schottky and Frenkel defects. Line defects, called edge and screw dislocations, control plastic deformation. Planar defects include grain boundaries, stacking faults, and twin boundaries. Volume defects include voids, precipitates, and second-phase inclusions. These defects govern mechanical, electrical, and optical properties in. Let us summarize this section. A crystal is a lattice combined with a basis, and there are 14 Bravais lattices. Miller indices and the reciprocal lattice make diffraction analysis tractable. Bragg's law links observed angels to atomic spacings. Defects, far from being rare exceptions, dictate the properties of nearly every real material. Typical exam questions include defining the basic units, deriving packing fractions, using Miller indices and Bragg's law. Our next section is on acoustics and ultrasonics, covering everything from concert hall design to medical imaging. Sound is broadly divided into three frequency ranges. The audible range covers about 20 to 20,000 Hz. Below 20 Hz lies the infrasonic range, used by some animals and observable in earthquakes. Above 20 kHz lies the ultrasonic range, used widely in medicine and non-destructive testing. The speed of sound depends on the elastic and inertial properties of the medium. In fluids, it is the square root of bulk modulus over density, while in solids, longitudinal speed. Architectural acoustics deals with sound behavior inside enclosed spaces. The reverberation time T60 is the time taken for the sound level to drop by 60 decibels after the source stops. It depends on the volume of the room and the total absorption from surfaces. Sabine's formula relates T60 to room volume divided by total absorption. Different uses require different reverberation times. A concert hall ideally has about 1.8 seconds, while a lecture hall needs only about. Real halls suffer from various acoustic defects. Echoes from distant reflections can be reduced with absorbers or irregular surfaces. Excessive reverberation is treated with acoustic panels and drapes. Focusing problems caused by concave surfaces can be avoided by design. Dead spots are eliminated by adding diffusers. Resonances and flutter echoes are tackled with varied absorption. External noise is blocked using soundproof. Ultrasonic waves can be generated by two main methods. Magnetostriction oscillators rely on the change in length of a ferromagnetic rod under an alternating magnetic field, and they typically operate up to around 100 kHz. Piezoelectric oscillators use quartz or PZT crystals driven by a tank circuit, producing high frequencies up to MHz with high power. These rely on the inverse piezoelectric effect, where an electric field Ultrasound is detected by several techniques. Piezoelectric detectors work as the reverse of generators, converting mechanical vibration into electrical signals. Thermal methods, such as Kundrat's tube, use standing wave patterns of dust. Sensitive flame methods detect pressure variations through flame deflection. Acoustical gratings in liquids exploit periodic density changes caused by ultrasonic waves. Each method suits different frequencies. Ultrasonics has wide engineering applications. Non-destructive testing of welds, castings, and rails uses pulse echo methods. Medical imaging in the 2 to 20 MHz range provides B-mode and Doppler images. Sonar enables underwater navigation and depth measurement. Ultrasonic cleaning and machining rely on cavitation. Process control applications include emulsification, degassing, and soldering. Therapeutic uses include high-intensity focused ultrasound and lithotripsy for. Let us summarize this section. Sabine's formula, with reverberation time proportional to volume over absorption, is the master formula of room acoustics. Piezoelectric and magnetostriction methods generate ultrasound at different frequency ranges. Non-destructive testing, medical imaging, and sonar are key engineering uses. Typical exam questions ask you to define reverberation time, derive Sabine's formula, discuss acoustic defects, describe ultrasound generators. We now study dielectrics and magnetic materials, the building blocks of capacitors, transformers, magnets, and many others. A dielectric is an insulator that polarizes in response to an applied electric field, storing electrical energy. The electric displacement field combines the applied field and the polarization. The relative permittivity epsilon r and the electric susceptibility Chi are related through epsilon r equals 1 plus Chi. Polarization is proportional to applied field, with the proportionality involving susceptibility and vacuum permittivity. These relations connect microscopic response. 4 polarization mechanisms contribute to a dielectric's response. Electronic polarization arises from distortion of the electron cloud relative to the nucleus. Ionic polarization comes from relative displacement of positive and negative ions. Orientational polarization involves alignment of permanent dipoles, important in materials like water. Space charge polarization occurs at interfaces between media of different conductivities, known as the Maxwell-Wagner effect. The total polarizability is the sum of. The Clausius-Mosutti relation connects the macroscopic relative permittivity of a nonpolar dielectric to the microscopic polarizability of its molecules and their number density. It is written as the ratio of epsilon r minus 1 to epsilon r plus 2 equal to n alpha over 3 epsilon 0. At optical frequencies, where epsilon r becomes the square of the refractive index, this becomes the Lorentz formula. It allows estimation of molecular polarizability. The relative permittivity of a dielectric depends on the frequency of the applied field. At low frequencies, all 4 polarization mechanisms contribute. As frequency increases, space charge effects drop out first, then orientational, then ionic, and finally electronic polarization. The graph shows this stepwise decrease. Each loss corresponds to the inability of that mechanism to follow the rapidly oscillating field. This frequency dependence is critical for designing capacitors, microwave components, and. A real dielectric has a complex permittivity with a real and imaginary part. The loss tangent, defined as the ratio of imaginary to real permittivity, quantifies the energy dissipated as heat. Dielectric strength is the maximum electric field a material can withstand before breaking down. Breakdown can be intrinsic, thermal, electrochemical, or defect-induced. Understanding losses and breakdown is essential for the design of insulators, transformers. Magnetic materials are classified by their susceptibility. Diamagnetic materials have small negative susceptibility and include copper, silver, bismuth, and water. Paramagnetic materials have small positive susceptibility, like aluminium, manganese, and oxygen. Ferromagnetic materials have large positive non-linear susceptibility, with iron, cobalt, and nickel as examples. Antiferromagnetic materials show small positive susceptibility, like manganese oxide. Ferrimagnetic materials have large positive susceptibility and include magnetite and ferrites. The relations between B, H, and magnetization summarize below the Curie temperature. The exchange interaction in ferromagnets aligns electron spins into regions called domains. Within each domain, magnetization is uniform, but different domains point in different directions. When an external field is applied, favorably oriented domains grow at the expense of others, and eventually all domains rotate to align with the field. Above the Curie temperature, thermal energy destroys this order and the susceptibility. The hysteresis loop is a plot of magnetic induction B against applied field H for a ferromagnetic material. When the field is reduced after saturation, the material retains some magnetization, called the retentivity or remanence. A reverse field, called the coercivity, is needed to bring B back to zero. The enclosed area of the loop represents the energy lost per cycle per unit volume due to domain processes. Hysteresis loops are characteristic fingerprints of ferromagnetic and magnetic materials are also classified by the shape of their hysteresis loop. Soft materials have low coercivity, small loop area, and low energy loss. They include silicon-iron alloys and ferrites and are used in transformer cores and inductors. Hard materials have high coercivity, large loop area, and retain magnetization strongly. Examples include alnico, neodymium iron boron, and ferrite ceramics used in permanent. Ferrites have the general formula Mo times Fe2O3, where M is a divalent metal such as manganese, zinc, or nickel. Their high electrical resistivity gives them very low eddy current losses at high frequencies. They are widely used in microwave isolators, circulators, RF transformer cores, electromagnetic interference suppression, and magnetic memory. Yttrium iron garnet and related garnets are particularly important in microwave components. Let us summarize this section. 4 polarization mechanisms operate at different frequency scales in dielectrics. The Clausius-Mosotti equation links micropolarizability to macropermittivity. Magnetic classification spans dia, para, ferro, antiferro, and ferrimagnetic materials. The hysteresis loop is the fingerprint of ferromagnets and ferrimagnets. Typical exam questions cover polarization types, the Clausius-Mosotti derivation, magnetic classification, hysteresis, and the comparison between soft and hard. We now move into modern physics, beginning with the structure of the atom and the hydrogen spectrum, where quantum mechanics found. The hydrogen atom emits and absorbs light at a discrete set of wavelengths. These wavelengths are described by the empirical Rydberg formula, which involves the difference of inverse squares of two integers and the Rydberg constant. The spectrum is grouped into series. The Lyman series lies in the ultraviolet, with the lower level at n equals 1. The Balmer series is in the visible, with the lower level at n equals 2. The Paschen, bracket, and PFUND. Niels Bohr proposed a model with two postulates. Electrons move only in stationary orbits where the angular momentum is an integer multiple of h bar. Transitions between orbits emit or absorb photons, whose energy equals the difference of orbital energies. For a hydrogen-like atom of nuclear charge Ze, the allowed radii and energies follow simple expressions. The Bohr radius is about 0.53 angstroms, and the ground state energy is minus 13.6 electron volts for hydrogen. The model reproduces the Rydberg formula and explains solving the Schrödinger equation in spherical coordinates separates the hydrogen wave function into radial and angular parts. 4 quantum numbers describe the state. The principal quantum number n takes positive integer values. The orbital quantum number L takes values from 0 to n-1, labeled S, P, D, and F. The magnetic quantum number m ranges from -L to +L. Finally, the spin quantum number takes values plus or minus 1/2. The energy depends only on n, with degeneracy n. Consider the transition from n equals 3 to n equals 2 in hydrogen. Using the Rydberg formula, the reciprocal wavelength is the Rydberg constant times 5/36. Solving gives a wavelength of about 656.3 nanometers. This is the famous H-alpha line, the dominant red line in the hydrogen-Balmer series. It is widely observed in astronomy, in solar prominences, and in plasma. The vector atom model adds spin to orbital angular momentum through LS coupling, giving total angular momentum J. Magnetic quantum numbers split levels in magnetic fields, producing the Zeeman effect. The Pauli exclusion principle states that no two fermions can share all 4 quantum numbers, and this principle is responsible for the structure of the periodic table. Allowed transitions follow selection rules involving changes in orbital quantum number, magnetic. Atomic spectra have many engineering uses. Spectroscopy techniques like atomic emission, absorption, and inductively coupled plasma optical emission perform elemental analysis. Discharge lamps and fluorescent lamps rely on atomic transitions for light production. Atomic clocks based on cesium and rubidium provide ultra-precise timekeeping. Astronomical observations reveal chemical compositions of distant stars and galaxies. In fusion research, plasma diagnostics use atomic spectra to monitor temperature. Our next section is nuclear physics, the study of atomic nuclei and the energetic processes that power stars, reactors. The nucleus consists of protons and neutrons, collectively called nucleons. The atomic number Z is the number of protons, the neutron number N is the number of neutrons, and the mass number A is the sum of the two. The nuclear radius scales as A to the 1/3, with a coefficient of about 1.2 femtometers. Nuclear density is approximately 2.3 times 10 to the 17 kilograms per cubic meter, and is essentially the mass of a nucleus is less than the sum of the masses of its protons and neutrons. The difference is called the mass defect, and when multiplied by c squared it gives the binding energy. The binding energy per nucleon is a key indicator of nuclear stability. It rises sharply for light nuclei, peaks around iron with a close to 56, and then slowly decreases for heavier nuclei. This curve is the reason why both fusion of light nuclei and fission of heavy. The semi-empirical mass formula treats the nucleus as a charged liquid drop. It includes 5 terms: a volume term, a surface term, a column term, an asymmetry term, and a pairing term. Each term reflects a physical aspect of nuclear binding. This formula successfully predicts trends in binding energy, the energetics of fission and alpha decay, and the optimal proton number for a given mass number. The number of radioactive nuclei decreases exponentially with time. The decay constant lambda is the probability per unit time for a nucleus to decay. The half-life is the natural logarithm of 2 divided by lambda, while the mean life is 1 over lambda. Activity, defined as decay rate, is measured in becquerels, with 1 becquerel equal to 1 decay per second. The older unit, the Curie, equals 3.7 times. There are several modes of radioactive decay. In alpha decay, a heavy nucleus emits a helium-4 nucleus. In beta- decay, a neutron converts into a proton, emitting an electron and an antineutrino, increasing Z by 1. In beta plus decay, a proton converts into a neutron, emitting a positron and a neutrino, requiring sufficient mass difference. Electron capture is another route. Gamma decay involves transitions between excited nuclear states. Release fission is the splitting of a heavy nucleus. For example, a neutron absorbed by uranium-235 forms an excited compound nucleus that fragments into barium and krypton with 3 neutrons and about 200 mega-electron volts of energy. Fusion is the combination of light nuclei. The deuterium-tritium reaction produces helium-4, a neutron, and about 17.6 mega-electron volts. Fusion powers stars and is the basis of thermonuclear weapons and is the goal of research reactors like ITER and the several detectors measure nuclear radiation. Geiger-Müller counters and ionization chambers are simple gas-filled devices. Scintillation detectors such as sodium iodide or plastic, combined with photomultiplier tubes, give fast response. Solid-state detectors like high-purity germanium and silicon offer excellent energy resolution. Bubble and cloud chambers were important historically. Accelerators include cyclotrons, synchrotrons, linear accelerators, and betatrons used. Nuclear physics has many engineering applications. Nuclear power generation uses pressurized water, boiling water, CANDU, and fast breeder reactors. Medical imaging and therapy include PET, gamma cameras, and radiotherapy. Industrial radiography uses gamma rays for non-destructive testing. Radiocarbon and isotope dating reveals ages of materials. Tracers help study environmental and biological systems. Radioisotope thermoelectric generators provide power. Let us summarize this section. Nuclear matter is nearly incompressible, with density essentially constant across all nuclei. Iron has the highest binding energy per nucleon, so both fission of heavier nuclei and fusion of lighter ones can release energy. Radioactivity follows an exponential decay law, with half-lives ranging from microseconds to 10 to the 20 years. Typical exam questions include deriving the radius formula, stating the semi-empirical mass formula, deriving the decay law, and distinguishing fission from fusion. We now study renewable energy physics, the science behind solar, wind, hydro, and other technologies that will power. There are several reasons we need renewable energy. Fossil fuel reserves are finite. Carbon emissions drive climate change. Energy security depends on diverse and local sources. Renewable resources include solar, wind, hydro, biomass, geothermal, and tidal energy. Engineering physics underpins efficient harvesting of each of these. Globally, renewable energy now represents more than 30% of new generation capacity in many regions, and this fraction A solar cell is essentially a p-n junction that absorbs photons of energy greater than the band gap. Each absorbed photon creates an electron-hole pair, which the built-in field separates, producing a photocurrent. An equivalent circuit models the cell as a current source in parallel with a diode and a shunt resistance, with a series resistance in the wire. The diode equation combined with the photogeneration term gives the cell's current voltage characteristic, showing how output current depends on voltage, illumination. Several parameters characterize a solar cell. The short circuit current is the current at zero voltage. The open circuit voltage is the voltage at zero current. The fill factor measures how rectangular the IV curve is, indicating quality of the cell. Efficiency is the ratio of maximum electrical power output to incident solar power. The Shockley-Quasar limit caps single junction efficiency at about 33%. Multi-junction cells can exceed 47%. Several solar cell technologies are in use. Monocrystalline silicon is the most widely installed, with lab efficiency around 26%. Multicrystalline silicon is cheaper, at about 23%. Thin film amorphous silicon achieves about 13% and is flexible. SiGs and cadmium telluride thin films give cost-effective performance around 22 to 23%. Gallium arsenide single-junction cells exceed 29%. Perovskite silicon tandem cells now cross 33%. Multi-junction 3-5 cells reach above 47% for space and the kinetic power available in wind crossing an area is half the density times the area times the cube of wind speed. The strong cubic dependence means even small speed changes greatly affect power output. The Betz limit states that no ideal turbine can extract more than 16/27, or about 59.3% of this kinetic power. Real wind turbines typically achieve a power coefficient between 0.4 and 0.5. Rated wind speeds are around 11 to 14 meters per second, with cut in around 3 and cut out around 20. Hydropower converts the potential energy of falling water into electricity. Power depends on water density, gravitational acceleration, flow rate, head height, and efficiency. Hydropower is the world's largest single source of renewable electricity. Tidal range energy extracts the potential energy difference between high and low water. Wave energy involves mechanical energy flux proportional to the square of wave height and the wave period. Devices include oscillating water columns, point absorber. Geothermal energy uses Earth's internal heat for direct heating or to drive turbines using binary, dry steam, or flash plants, often with capacity factors above 90%. Biomass energy is obtained through combustion, gasification, or anaerobic digestion and is carbon neutral when sustainably sourced. Hydrogen is a versatile fuel of the future. It is produced through electrolysis, especially using surplus renewable electricity, and used in fuel cells where the only energy storage technologies span a wide range. Batteries include lithium-ion, lithium polymer, flow batteries, and sodium-ion variants. Pumped hydro currently accounts for about 95% of global grid storage. Compressed air energy storage uses underground caverns to store air. Flywheels and supercapacitors provide rapid power on short time scales. Thermal storage in molten salts is used in concentrated solar plants. Hydrogen acts as a chemical energy carrier. Each option faces engineering challenges in round-trip efficiency, Let us summarize this section. Solar photovoltaics convert photons to electrons via a p-n junction, limited by the Shockley quasar bound for single junctions. Wind power scales as the cube of wind speed, with the Betz limit constraining extraction. Energy storage and grid integration form the most active engineering frontier in renewable energy. Typical exam questions include deriving the solar cell IV equation, defining fill factor and efficiency, deriving the Betz limit, and discussing the physics of energy. Our next section ties together everything we have studied and explores how engineering applications transform fundamental physics into engineering physics bridges fundamental principles and practical hardware. Classical mechanics underpins MEMS sensors and accelerometers in modern smartphones. Quantum mechanics enables tunnel diodes, flash memory, and quantum bits. Optics drives lasers, fibers, displays, and cameras. Electromagnetism powers motors, generators, antennas, and MRI scanners. Solid-state physics makes CMOS chips, GPUs, and sensors possible. Thermodynamics underlies engines, refrigerators, micro and nano electromechanical systems are miniaturized machines fabricated using integrated circuit-compatible processes. Accelerometers detect motion for airbag deployment and gaming. Gyroscopes stabilize drones and smartphones. Pressure sensors and microphones are found in countless devices. Lab-on-a-chip biosensors enable rapid diagnostics. Radio frequency MEMS provide filters and switches. The underlying physics involves simple harmonic motion, beam mechanics, and capacitive. Several display technologies are in use. Liquid crystal displays use birefringence and polarizers but require a backlight. LEDs and mini-LEDs emit light directly from semiconductor junctions. Organic LEDs use organic semiconductors and are self-emissive and flexible. Micro-LEDs are arrays of small inorganic LEDs with feature sizes below 50 micrometers. Quantum dot LEDs use size-tuned quantum dots for excellent color purity. The physics involves polarization, electroluminescence. Medical imaging makes extensive use of physics. X-ray computed tomography uses absorption tomography to map internal structures. Magnetic resonance imaging exploits nuclear spin precession in strong magnetic fields. Ultrasound imaging relies on piezoelectric transduction. Optical coherence tomography uses low-coherence interferometry for high-resolution imaging of tissues. Positron emission tomography detects gamma rays from positron annihilation. Hyperspectral imaging extends biomedical diagnostics. Modern communications and computing rely on a wide range of physics. Optical fiber networks use erbium-doped fiber amplifiers and dense wavelength division multiplexing. Wireless systems include 5G millimeter wave, MIMO antennas, and beamforming. Quantum communication and quantum key distribution, including the BB84 protocol, offer fundamentally secured links. Photonic integrated circuits combine optical components on chip. Spintronics uses giant and tunnel magnetar systems in hard disk read heads. Quantum computing platforms include superconducting qubits. Let us summarize this section. Every engineering domain rests on physical principles. Modern devices increasingly merge classical and quantum physics. Cross-disciplinary fluency multiplies an engineer's design space. Typical exam questions include discussing MEMS technology, comparing LCD, LED, and OLED display technologies, describing the physical principles of MRI, and explaining spintronics. This slide lists the fundamental physical constants used throughout the course, based on the latest CODATA values. These include the speed of light, Planck constant and its reduced form, elementary charge, rest masses of the electron, proton, and neutron, the Boltzmann constant and Avogadro number, the gas constant, permittivity and permeability of free space, gravitational constant, Stefan Boltzmann constant, Rydberg constant, Bohr radius, Bohr magneton, fine structure constant, and the atomic mass unit. Keep these values. This slide provides commonly used conversion factors. 1 electron volt equals 1.6 times 10 to the minus 19 joules. 1 calorie equals 4.184 joules. 1 atomic mass unit corresponds to about 931 mega electron volts of energy. An angstrom is 10 to the minus 10 meters, while a Fermi is 10 to the minus 15 meters. 1 barn is 10 to the minus 28 square meters. Atmospheric pressure, horsepower, and astronomical distances like light year and parsec are also. This formula sheet summarizes mechanics and oscillations. It includes the standard SHM solution, energy in SHM, the damped SHM equation, and the quality factor. The general wave equation is given, with the longitudinal Doppler formula for light, and the relation between group and phase velocities. These formulas are essential for problem solving. This sheet lists key optical formulas. It includes the Young's double-slit fringe width, thin film constructive condition, Newton's rings dark ring formula, single-slit minima, grating principal maxima, Rayleigh resolution, Brewster's and Malus's laws, fiber numerical aperture, and the V number condition for single-mode propagation. These cover the entire optics section of the course and are useful references during. This sheet collects quantum and atomic physics formulas. The de Broglie wavelength, Heisenberg uncertainty relation, time-independent Schrödinger equation, particle in a one-dimensional box energy and wave function, hydrogen energies and the Rydberg formula, Bohr radius, Compton shift, and Planck's radiation law are all included. Keep these at hand for quantum mechanics. And this sheet summarizes formulas from solid-state physics. Bragg's law, the cubic interplanar spacing, Fermi-Dirac distribution, intrinsic carrier density, law of mass action, Hall coefficient, and Shockley diode equation are listed. For superconductivity, the BCS energy gap relation, London penetration depth, and flux quantum are included. These provide a compact reference for solid state. This sheet summarizes electromagnetism and special relativity. Maxwell's equations in vacuum are written in differential form. The speed of electromagnetic waves and their intensity are stated. For special relativity, the Lorentz factor, time dilation, length contraction, energy momentum relation, and velocity addition formula are included. These form the backbone of any electromagnetism. Physics uses Greek letters extensively as symbols. This table pairs each Greek letter with its physics meaning. For example, alpha is used for fine structure constant and absorption coefficient. Lambda is used for wavelength and decay constant. Omega is used for angular frequency and ohm. Psi is used for wave function. Knowing these conventions helps you read physics literature efficiently through. This slide lists the mathematical operators we use most often. The gradient describes spatial change of a scalar field. The divergence measures the local source strength of a vector field. The curl measures rotational tendency. The Laplacian is the divergence of the gradient. The D'Alembertian generalizes this to spacetime. Commutators capture quantum non-commutativity. Expectation values, inner products, and the Dirac delta function. Here is the detailed bibliography for further reading. It includes Halliday-Resnick-Walker for fundamentals, Beezer for modern physics, Griffiths for electrodynamics and quantum mechanics, Ghatak for optics, Kittel, Ashcroft-Mermin, and Pillai for solid-state physics, Pandey Chaturvedi and Malik Singh for engineering physics, Tipler-Llewellyn for modern physics, SZE and Streetman for semiconductors, Crane for nuclear physics, Tinkham for superconductivity, Poole for nanotechnology, Jackson for advanced electrodynamics, French for vibrations and waves, Cullity for X-ray diffraction, and Saleh Teach for photonics. Consult these books to deepen your understanding. Thank you for completing this course on engineering physics. We have traveled from classical mechanics and oscillations through optics, quantum mechanics, solid-state physics, electromagnetism, relativity, and modern materials, and finally to applications such as renewable energy and advanced devices. Physics is the poetry of nature, written in the language of mathematics. It is also a continuum. Classical, modern, quantum, and nano are not separate worlds but a connected whole. Best wishes for your examinations. Engineering physics opens the door to every branch of